New topics known as Carnot Engine. It was the first engine invented by what you can say a model of engine given by Sir Carnot, which is taken to be an ideal engine, whose efficiency is considered to be 100%. Is it clear? So now, what are the parts of the engine we should know? There are different parts of the engine. Body of the engine, which consists of an ideal gas. Here it consists of a source whose temperature is so high that whatever of the amount of heat is taken from it, its temperature never decreases. There is a sink in which is very low, its temperature is very low. Whatever amount of heat is given, its temperature never decreases. So it will never increase. And another one is the insulating stand. So these are the four parts of the engine, and it consists of an ideal gas. This body of the engine is three sides of insulating. This is movable, piston is there, and base is conducting. At first, what we will do, we will place the source of the engine, we will place the body of the engine on the source. Now, the temperature of the source and the body of the engine becomes same. So as it becomes same, so what will happen? It will get some heat and it will expand. This body of the engine, this piston will expand, and we will get what? Due to the expansion, what we will see? We will get what? Some work done is there. As the temperature of the system here remains constant, when it increases, volume increases, pressure decreases, so the process is what? Isothermal expansion. And graphically, when you see that how it's represented in graph, you will see that in graph it will start from P and it will go to where? B, and the volume increases, but the pressure decreases. So we can say temperature remains constant. So it is an isothermal expansion of the volume, isothermal expansion of the system, and this work done is given by the graphical area of the graph from A, B, G, E. This area will give you the area of the isothermal expansion in graphical map. But when you go to the analytical method, it is a different case. But we have taken, we have taken the vessel is there. In that vessel, some amount of work is done. Suppose that dW is the amount of work done in changing the volume dV. Okay, what is the amount of work done? dW is the amount of work done in changing the volume dV. Then what is work done? Then dW is equal to PdV. Is it clear? Work done is how much? dW is equal to PdV. Now, therefore, total work done in changing the volume from V1 to V2 is given by W1 is equal to how much? W1 is equal to integration from V1 to V2 PdV. Is it clear? Since PV equal to RT1, so it means that P equal to RT1 by V. Therefore, W1 is equal to integration from V1 to V2 RT1 by V. dV is equal to RT1 integration from dV by V, V1 to V2. So RT1 log E, V2 by V1. So we'll get, by integration we get, by putting the value we get W1 is equal to RT1 because the temperature is T1, log E V2 minus log E V1. So it comes at RT1 log E V2 by V1. This is the expression for work done, analytical expression for work done in isothermal process. Now, the next task is what? We will place this body of the engine, we will remove from the source and we will place somewhere on the insulating stand. Now you see, all the sides becomes, when you place it on insulated, all the sides will be what? Insulated. No heat can enter inside, no heat can go out from it, and still the expansion is continuing. That means what? Volume of the body increases, pressure decreases, temperature changes. Suppose temperature changes from T2 to T3, volume changes from V2 to V3, pressure changes from P to P3, but heat remains constant. It will not go anywhere else. So what we can say, this process is an adiabatic process. This process is an adiabatic process. And in this process, in graph you will see that it will move from here, it is moving from here, P2 to B to C. So the work done in graphically the area of BCAG will give you the adiabatic work done. Area BCAG will give you the adiabatic work done. Now when we go for adiabatic expansion, that is second stroke, adiabatic expansion is there. The graphically we get the idea. But when we go for analytical treatment, in analytical, W2 is in the integration from V2 to V3 PdV. And as PV to the power gamma equal to K, so we can say P equal to how much? P equal to K by V to the power gamma. So we can say W equal to how much? Integration from V2 to V3 K by V to the power gamma dV. It is how much? K by V2 to K by V to the power gamma dV. Yeah. So W2, the result is W2 is equal to K into V2 to V3 V to the power minus gamma dV. It will be how much? K. Integration of V to the power minus gamma will give you what? V to the power minus gamma plus 1 divided by minus gamma plus 1. So it will be V2 to V3. So we'll get W2 is equal to K by 1 minus gamma. Integration, this result will be what? 1 by V to the power gamma minus 1 V2 to V3. Now when you put the value of V2 to V3, it will be what? 1 by V2 to the power minus gamma. Gamma minus 1 minus 1 by V2 to the power gamma minus 1. And as you know, PV is equal to constant, so we can write that P2 V2 is to the power gamma is equal to P3 V2 is to the power gamma is equal to K. So we will get what? So we will get the result as 1 by 1 minus gamma K by V2 to the power gamma minus 1 minus of K by V2 to the power gamma minus 1. So 1 by 1 minus gamma, we can put instead of K, we can put P3 V2 to the power gamma divided by what? V3 to the power gamma minus 1 minus of P2 V2 to the power gamma P2 V2 to the power gamma minus 1, and the result is that 1 by 1 minus gamma P3 V3 to the power gamma minus gamma plus 1, and here it is the minus of P2 V2 gamma minus gamma plus 1, and as the whole result will be how much? W2 is equal to 1 by 1 minus gamma P3 V3 minus P2 V2. As you know, P2 V2 is equal to how much? P2 V2 is equal to R, PV is equal to RT. We know that PV is equal to RT, so we can write P2 V2 is equal to RT1, and P3 V3 is equal to RT2. So we can put W2 is equal to how much? 1 by 1 minus gamma RT2 minus of RT1 K R by gamma minus 1 is T1 minus T1. Here we have taken already T2 minus T1, that means 1 minus gamma. But as it is T1 minus 2, we have taken the minus common. And minus are common, and here we make it what? Gamma minus 1. So the result is how much? R by gamma minus 1, T1 minus T2. Clear or not? I think it is clear. Our next step is what? We will place this body of the engine on the sink. What will happen? It will release heat to it. When it releases heat, its volume will decrease and its pressure will increase. Is it clear? So as the volume will decrease and pressure is increased, so the temperature due to sink is remain constant. So we can say, suppose the temperature becomes T2, so we can say it is a process of isothermal compression. And in graph, you can say that area of which one? Isothermal compression is C D F H. C D F H will give you the isothermal compression. W3, the work done in the graphical area. Graphically, it will be seen by like this. Okay. But when we go to the work, you see, now when when you go to analytical treatment is so that W3 is equal to RT2 log E V3 by V4. Is it clear? And when again what we do, we will remove from this one, and again we will what? Place it on the insulating stand. Now what is happening here? Everything is what? Again on the insulated system. That means volume will decrease, pressure will increase, temperature will increase compared to original temperature T1, but no heat can go out and no heat can be given inside. So the process is adiabatic compression. Volume is decreasing, so it is known as what? Adiabatic compression. So here you can see this fourth stroke is adiabatic compression, and the area is given by which one? Area will be given by ADFE. This area will be given with ADFE. We can say DAEF, that area is there. And analytically we will get what? W4 is equal to R by gamma minus 1, T2 minus T1. This will be minus because what? Compression is there. Okay. And when you take minus, common taken out minus, there will be R by gamma minus 1, T1 minus T2. Now, the total heat will be converted into work. This total heat is converted into work. So W is equal to how much? W1 plus W2 minus W3 minus W4. So area ABGE plus area BCHG minus area CDFH minus area ADFE. So total area is what? Area ABCD. Okay. This is graphically. Now when you go for the analytical treatment, you will see that analytically W1 is equal W1 plus W2 minus W3 minus W4. So it will be how much? R T1 log E V2 by V1. This is R by gamma minus 1, T1 minus T2. And after that it will be how much? Minus of R T2 log E V3 minus V4 minus of R by gamma minus 1, T1 minus T2. And we'll get what? And we'll get RT1 log E V2 by V1 minus of RT2 log E V3 by V4. So this is the amount of heat given and this is the amount of heat compressed. So this is what Q1, this is Q1 and this is what Q2. So it will be Q1 minus Q2. This amount of heat is given, this amount is released in the sink. So it will be total work done is Q1 minus Q2. Now, as we know, this B and C are in the same adiabatic. So we can say that what? T1 V2 to the power gamma minus 1 is equal to T2 V3 to the power gamma minus 1. Because the temperature in B is how much T1, volume in B is how much V2, temperature in C is how much T2, volume is V3. So T1, we know the formula Tv to the power gamma minus 1 equal to constant. So we can write what? T1 V2 to the power gamma minus 1 equal to T2 V3 to the power gamma minus 1. It implies that T2 by T1 is equal to V2 by V3 gamma minus 1. Again, as same, this one, your A and D are in the same adiabatic. This is your A and D are in the same adiabatic. So what we can say? We can say that this T4, this is what? T4 to the T2 V4 to the power gamma, T2 V4 to the power gamma minus 1 is equal to how much? T1 V1 to the power gamma minus 1. So we can get what? T2 by T1 is equal to V1 by V4 to the power gamma minus 1. As a result, what we will get? V2 by V3 gamma minus 1 is equal to V1 by V4 to the power gamma minus 1. And we get what? V2 by V1 is equal to V3 by V4. So, hence from equation, this equation 1, we can write what? W is equal to RT1 log E V2 by V1 minus of RT2 log 2 RT2 log E V2 by V1. So if you take common log E V2 by V1 R, you will get R by T1 minus T2. Now friends, we should know about the definition of efficiency. What is efficiency? Efficiency of an engine is given by what? Amount of heat, amount of work done given to the ratio of amount of work done to the amount of heat given. What is the amount of heat? Amount of work done is W. What is the amount of heat given is Q1. So we can write R T1 minus T1 T2 into log E V2 by V1. And given amount of heat is R T1 log E V2 by V1. These two will cancel out. We get what? 1 minus T2 by T1. So from there, as we know, the temperature of T2 never increases. T1 is very high. So the result is always what? This will become 0, so you will get what? Efficiency is 1. This is the case of isothermal expansion. This is the case of Carnot engine. But it is a model engine, so it has some limitation. In practical cases, all the engines, maximum efficiency is about 59 to 60%. And why? So there should be some limitations are there. Still in practical, there are no gases taken to be ideal. Only one gas, hydrogen, is very closer to the postulates of kinetic theory, which is known as what? Ideal, which will be considered as ideal. So it is wrong conception that it is an ideal gas is there, ideal engine is there. Another demerit is there. It has the sources say that the source is so high temperature that whatever amount of it is taken, if the temperature never decreases, no such source is made till today where the temperature becomes temperature decreases. Again, it is the thing. whose temperature is so low that whatever amount of heat is given, its temperature never increases. It is also a wrong concept, because why? Still today no thing is practically found that whose temperature, where the heat is given and its temperature never increases. So these are the limitations of what? Our Carnot engine. And we know that some limitations of first law of thermodynamics are there. By viewing this, we have come to know what they have given second law of thermodynamics. Sorry, what are the second law of thermodynamics? The second law of thermodynamics is generally what we can say. Second law of thermodynamics is generally the overcome of limitations. How the limitations can be overcome by what? Or limitations of first law can be overcome by the second law. There are three statements given by three scientists. One is known as Clausius statement, other one is known as Kelvin statement, and third one is known as Planck's statement. How many statements are there? Three. One is known as Clausius statement, second one is known as Planck's Kelvin statement, third one is known as Planck's statement. Kelvin's what is Clausius statement? It states that heat cannot flow from what? Cold body to hot body without the performance of any external work. We can say that heat cannot flow from cold body to hot body without performance of work by some external agency, which is known as Clausius statement. Second statement is that Kelvin statement. It states that it is impossible to obtain continuous supply of heat by cooling a body below the temperature of surroundings. Continuous supply of heat we cannot get by cooling the body below the surrounding temperature. Below the coldest of the surrounding. Okay. Third one is that it is impossible to extract all the amount of heat from a body and to convert it into what? So these are the three laws. First statement is what? Clausius statement. Second statement is what? Kelvin statement. Third one is the Planck statement. Clausius statement states that what are the states? It cannot flow from a cold body to hot body without the performance of external work. Second is what? Kelvin statement. It is impossible to obtain continuous supply of heat from a body by cooling the body below its surroundings. Third is what? We cannot convert whole amount of heat into work from a single body. Is it clear? So these are the second law statement. So up to this much is to discuss. Next class we will discuss about the new chapter. Thank you everyone.